Today we continue to talk about normal distribution. So let's start with the notes. At first we'll have a bunch of definitions and kind of almost meaningless formulas, but then it'll make sense. So z-score is the number of standard deviations a specific data point is away from the mean. Right, so think histogram or the bell curve, right? And we have the mean, and we have a specific data point, and we want to know how far the data point is away from the mean. So we calculate this distance divided by the standard deviations. How many standard deviations this point is away from the mean? So obviously the formula is just take your observation x, subtract the mean mu, and then divide by the standard deviation. That's your z-score. A positive z-score means that the data point is where? On the left or on the right of the mean?
The left?
Right.
The right.
On the right of the mean, right? Because it has to be larger than the mean. So, right. And the negative z-score means the data point is on the
Left.
So negative z-score means the data point is on the left of the mean. So just to practice using the formula, let's do these two simple problems. Given the following information, find the missing value, set up each equation, and round to 2 decimal places. So the formula is the z-score equals x minus mu divided by sigma. If I know my mu, I know my sigma, and I know my x, I can figure out the z-score. So z equals 11.5 minus 7 divided by 2. And if I enter this whole thing into calculator, what I have is 2.25. Just using the formula. Questions? This is the z-score. So it means that if we have a distribution with the mean 7 and standard deviation 2, the point 11.5 is over 2 standard deviations away from the mean, right? So it will be very far from the mean, more than 2 standard deviations away. Okay, number 2, same formula, z equals x minus mu divided by sigma. Now I have mu, sigma, and z, and I need to find x value. So I have to substitute all the values that I have into my formula. So here is z, negative 2.5 equals, my x is not known, so I'll just keep it as the variables, minus mu is 21 divided by sigma, which is 4.
X equals 11.
I don't know what my x equals, right? This is what I need to find.
11.
So now we just need to solve the equation. Huh? Yes, multiply by 4, multiply by 4. So negative 10 equals x minus 21. Now plus 21 on both sides. And what I have is x equals 11. So again, if I know my distribution has the mean of 21 and the standard deviation is 4, then 2.5 standard deviations below the mean is the data point 11. Make sense? Next one, a real life example. The weights of American males in pounds are given to us, and the weights of British males in kilograms is also given to us. Using your calculator, calculate the standard deviation for both the American and British males. So let's enter this whole thing into calculator. and find the standard deviation and the mean. Do I need to do this on the board? Okay. Okay, so remember how we enter our data? We go to Stat, Edit. We enter data in the first column. So I'll just clear everything. And now my data for the American males. 191, 249, 155, 75. So I entered the data for the American males, and now I'll calculate statistics. So I go Stat, Calc, and then the first one, the statistics for my first column. Here are my statistics for the American males. So for American males, I have the mean 201 pounds, and then standard deviation is 23 pounds. Well, let's keep the two decimal points. 201.43 and then 23.05. Everybody got the same numbers? Okay, so let's do the same thing for the second population of males, the British one. So Start, Edit, I'll just and start over. 85, 4, 19, 79, 95. Once we are done, we go to Start Calc and then statistics. So for the British males, I have the mean 87.57 kilograms, and the standard deviation is 4.89. Very good. Questions? Okay, so on the other half of the on the other side of the page, we have the second half of this problem. Over Thanksgiving dinner, my dad, American, and my Uncle Charlie, British, were having an argument over which person was more overweight. My dad is 225 pounds, and Uncle Charlie is 92 kilograms. Find z-score for my dad and Uncle Charlie, and then based on the z-scores, determine who is more overweight within their population, right? British versus American. So for my death score, we need to consider American male population, and so the mean for that was 200. So for American, the mu was 201.43. I'm rewriting because it's easier for me, and sigma was 23.05. And for the British population, we had a mean of 87.97 and the sigma 4.89. Okay, so let's figure out the score for each of them. So for my dad, Z equals 225, that's his weight, minus 201.43 divided by 23.05. And if we calculate this, this would be, check our math,
87.5. I don't know if that's what you were trying to. Oh, no, hold on.
Z-score.
I'm just talking about, right? That's a 9.
For the Charlie?
1.02. No, I'm just saying you wrote something.
Oh, incorrectly?
Yeah, she's
Right
like
here?
5.7.
Oh, it's 5.7.
Yeah.
Where'd you get 225 from?
My data is 225,000,
Oh,
right? So
okay.
that's the data point, my x,
Okay.
for which I'm calculating the z-score. Okay? So for my dad, I'm using the statistics for American males, and for my uncle, I'm going to use the statistics for the British males. So the dad z-score is 1.02. For Uncle Charlie, the z-score would be based on the British population and his weight, 92 kilograms minus 87.57 divided by 4.89, which is I have 0.91. You think? So right here, I have the bell curve. It's not labeled, right? Because I'm using the same bell curve for two different populations of males, so I don't want to put any numbers on it specifically, right? So the mu will be different and the standard deviation will be different for both populations. However, on this generic curve, I can place the z-score, or I can place the values for both Dad and Uncle Charlie just based on the z-score. So Dad's value or Dad's weight will be 1.02 standard populations from the mean, so it will be somewhere here. This is my dad, right? So it's one, or just a little bit over 1 standard deviation away from the mean on the right because the z-score is positive. Make sense? Right? And then for Uncle Charlie, the z-score is just under 1, so it's within 1 standard population from the mean in his population. So this would be my Uncle Charlie. So if we are considering, how overweight they are within their own population of males, who is more overweight? My dad. Perfect. So the dad is more overweight.
Bless you.
Bless you. But again, only if we consider him within the population of American males, right? We don't have the perfect male or average weight for the male across two countries. We are thinking about populations as separate populations, right?
So don't they, because they measure their weight differently, doesn't it matter?
What do you mean? Okay, so the next page, I guess. No, same page. Using these scores to find probabilities and percentages. So besides determining values distance from the mean, this score is associated with probability,
Where is this on the packet?
oh, just below the probability.
No?
It's formatted a little bit different on your page. And percentile.
Oh. Do you just want us to write those two things?
Yeah?
Okay. At the bullet points?
Mm-hmm. Oh, and then you don't have this. So this score is very useful when we want to understand how probable the data is or which percentile the value falls into. So this is how we are going to do this. Table method. Next page. Once you have calculated the z-score, the table is used to indicate what percentage of the data is to the left of the z-score on the normal curve. The table that we are talking about is the table on your formula sheet.
This one?
Well, this table is just part of it. So remember on that pink formula sheet, there is this table. There's a lot of numbers in it. You still have it?
Mm-hmm.
Yes, so take it out. You will use it. Round your z-score 2 decimal points. Whenever you are calculating your z-score, round it to 2 decimal places before you start using the table. Write it down. It is important. So now this is how we will use this table. Given the z-score of negative, this is just example. Given the z-score of negative 1.25, go to the line for negative 1.2. This is your table. If my z-score is negative 0.25, I look at the first decimal point only at first, and I find negative 1.2 in the rows right here, in the very left column, negative 1.2. And then in the first row, I find the 0.05. I go down and to the right, find the intersection. This number in this cell, that is the intersection of the two numbers, is 0.1056. This number is the let's go this way. Yeah, the value is 0.1056. So this number means that the probability of falling below a z-score of negative 0.25 is 0.1056. So if you think about the bell shape of our normal distribution, and we have a mean, right? The z-score negative 1.25 means that the value of this observation is 1.25 standard deviations on the left from the mean, right? So this is 1, 2, 3, 1, 2, 3. So somewhere over here is negative z-score negative 1.25. If I take all the data on the left of this point, the probability to fall below this value is 0.1056, which is 10.56%, right? The probability of falling below this point is 10.56%. Or we could also say that the z-score of negative 1.25 is at the 10.56 percentile. And it kind of makes sense, right? Remember, with what we learned last time, all these probabilities and percentiles are kind of related to how far away in standard deviations I am from the mu, right? So the data table or the z-score table, this table just lets you to be a little bit more precise about your points than the empirical rule. The empirical rule only divided our bell into 6, well, 7 lines, yeah, 6, 9, 9 on the left, right, yeah, into 9 sections. But the table allows you like very, very precise calculations. Questions about this? If there are no questions, let's practice. Find the percentage of data that falls below the following z-scores. So if your z-score is negative 2.89, what is the probability of falling below?
Yeah, but what number is it going to on the top?
Right. So if the z-score is negative 2.89, in the column I need to find, in my column I need to find number negative 2.8, and in the first row I need to find the number 0.09.
Oh.
Then you go down and to the right, and the cell that is in the intersection will be your answer. What is that answer?
0.0019. Is that it?
Let me put it here. So it's 0.0019. Yep. Yep.
How did you get the
What percentage is
0.09?
that?
I'm looking at my z-score, negative 2.89. First, I look at only this first decimal point, negative 2.8. And then the rest is, if I kind of stick, the last 0.09.
So 2 would be 01.
The remaining. So the answer for this question, the probability of falling below this z-score is 0.0019, which is in percentages 0.19%. So it's less than 1%. The probability of falling below this z-score in the normally distributed population is less than 1%, 0.19%. Questions? Okay. So let's do the next one. For the z-score 3.21, am I going to the right or to the left of the mean? To the right of the mean. So for this score, the probability of falling below this score would be what?
0.0007.
So I need to find the row 3.2 and I need to find the column 0.01, right? In the intersection, I will find the cell 3.201.
0.9993.
So the O is in here. What is it?
It's point.
0.0007.
No, it's 9993.
Yeah, it should be more there, right?
Yeah.
Because everything
Oh,
below
I
is like
got
almost the whole population. Almost the whole population.
It's 0.9993.
0.9999.
Where's your 0.9993?
1 minus
Where's your 0.999?
You gotta use
Oh,
your pink
I-
chart. Use your pink paper.
Okay, so yes, the sign is very important. But Isaiah, even though you got different number the first time because you looked at the negative 3.21, right? Because the distribution is very symmetric around the mean. Think about it. If I look at the z-score 3.21 and you looked at the z-score negative 3.21, Isaiah, everything to the left of my data point, right,
That we could see.
will be 1 minus everything to the left of yours.
That leaves 0.
Yep, exactly. So it's very symmetrical, so you can kind of play around with it. Not that it's any questions about this?
So is it 99.93 percentile?
Yes.
Yes.
Okay, next one. You can also find the probability of falling above with this score. Oh, as we just did, right? We kind of talked about this already. So if the total area under the curve is 1, right, you have, like, observation has to be somewhere under the curve. To find the probability greater than a z-score, you use the table to find the probability of the z-score and then subtract that probability from 1. Kind of makes sense again, right? So if I have my bell and I have my z-score right here, my z-score z, the probability of falling above the z-score is just 1 minus the probability of falling below it, right? Because the probability of falling somewhere is 1, right? If you choose the data somewhere in the population. So it's 1 minus the probability of falling below the z-score. Question? Does this make sense? Yeah? Okay. So let's practice. Find the probability of falling above the following z-score. Z-score equals negative 0.04. So the probability of falling below 2L or 1. 2 below 2L's or 1?
Yeah.
Oh, sorry. So let's look at our table. The probability of falling below the z-score of negative 0.04 is, I have 3, 4, 4, 6, correct? Agree? So I'll just look at the chart, right? I'm looking for the row negative 0.4 and then the very first column because I don't have.
I have a question.
No, that's wrong.
Shouldn't it be
Yeah, this is wrong. This is wrong.
Shouldn't it be 0.4840?
Yeah, it should be point.
No, it's
4840.
4840. Haha.
4840. Yes, Mary, you're right. Right?
Okay.
Because first I'm looking for the row negative 0.0, which is the very last row, and I'm looking for column 0.04, which is the fifth column. Yeah. Okay, so the probability of falling above this z-score will be what? 1 minus 0.484, which is 0. 0.5 what? 0.516. Yep, and that would be our final answer. So the probability of falling below the z-score we can find from the table. Just be very careful when you see that I made, and then the probability of falling above it would be just 1 minus. Questions? Okay, you do the next one by yourself. Should I just write the answer?
Yeah.
To compare? Okay, so the probability is 0.0179.
How?
No?
No, it's 2.1, and then because there's no extra number behind it, it should be 0. That you go under.
Okay, so this is for above. Probability of falling below will be 0.98. And now I can see
2-1.
2-1, yes.
Okay, now I got it right.
And probability of falling above would be 1 minus 0.9821, which is 0.179. Yeah? Questions? Okay. Oh,
No, there's something in between.
wait, there's a between. There should be a between, right?
There is.
Okay, so let's read one more. So who can tell me how to find the probability of falling between two?
Do you
Points.
find the probability of both first?
Yeah. So if I want to find the probability of falling between Z1, the Z-score Z1 and the Z-score Z2, right? I want to find the probability of falling right here. How would I find it?
Is that?
Take the big one, subtract the small one, right? So let's do the next problem number 5. Find the probability of falling between the two z-scores. The first z-score is negative 1.32, so we are on the left of the mean, and the second z-score is 2.43, which is on the right of the mean. So the probability of falling below this one equals, I have 0.0934 And the probability of falling below the other one I have 0.9925. So the probability of falling in between should be 0.9925 minus 0.0934, which is
0.05.
oh, something is wrong here. Am I looking at
We don't need to go above, just below.
points? What is it? 89?
Yes.
91. Yep.
Hold on, did you say put 0.9925 minus the volume?
Yep. Questions about this? So I have 0.6664 minus 0.0029 equals 0.6635. This is what I have for number 6. Check if you have the same.
I got 0.6635.
Correct. So let's start looking at the examples.
That's
Example
not on
word
there.
problems.
That's not good.
This is not yours?
No.
You don't have this?
Nope.
Do you have this?
No.
No.
You have this?
Yes.
Yes.
Okay. National Achievement Test is administered annually to 7th graders. The test has a mean score of 120, standard deviation 12. If the merited z-score is 1.25, what was her score on the test? Let's think about it, right? Do we need to use table for this? No, there is nothing about probabilities or percentages, right? Nothing about that. This is not the table kind of word problem. How do you find this? Yes, we need to use the equation. So the z-score, remember, is the x minus mu, how far away from the mean I am, in standard deviations, right? So I do know my z-score, I do know my sigma, and I do know my mean. I can figure out my x, the observation. So let's do that.
Got it.
You got it?
No idea.
So my z is 1.25 equals my x, I don't know, so x, and then my
I got it, but it doesn't make sense.
mu is 120 over, and my sigma is 12.
Wait, I did it right, but that doesn't make sense. I just get 135.
What do you mean?
How can you get 135 on that test?
Well, like SATs are 600, right? Or something.
Oh, I thought it was
It's
like
not just 100 kind of, yeah. So now it's just solve for x, yeah. Times 12 times 12. We are still working, 1.25 times 12 is what?
15.
15 equals x minus 120. So plus 120 plus 120. And we have x equals 135. So the score that Meredith got on her test is 135. Questions about this problem? Okay. Let's do this on the board because it's different, right? So the running times for a group of 200 runners to complete a 1 mile run are normally distributed. So we have our bell with the mean 6.5 and the standard deviation of 1.5 minutes. So mean is 6.5 and standard deviation is 1.5 minutes. Approximately how many of the runners have a time greater than 8 minutes? Well, these kind of problem we can actually solve with empirical rule or with our data with our z-square table, right? If I mark the mean on my bell curve and then I go one standard deviation above and below, 6.5 plus 1.5 gives me exactly 8, right? So the question is, how many of the runners have a time greater than 8 minutes? So everything above, just one standard deviation above mean. So I could actually use the empirical rule for this, right? So what would be my answer using the empirical rule? Well, it's very simple, right? Because half of my distribution is 50%, and then right here is 34, correct? So it's 100 minus 50 and minus 34. Agree? If I use empirical rule. Half of my population is on the left of the mean.
I got the answer.
And then within, from the mean to mean plus one standard deviation is 34%, correct?
Isn't it 100?
Huh?
100.
What do you mean? No, cannot be. Half. Half of the people, no. Half of the people would be above the mean. This is very symmetrical. We need above 8.
Don't you need to find the z-score first?
No. So these kind of problem could be found using the empirical rule,
Uh,
right? Because 8 is exactly one standard deviation away from my mean.
32.
Do we agree?
Is
So,
it
yes.
okay if I use the z?
Yes, it's okay to use this. So I just want to compare. 100 minus 50 minus 34 is 16%. So 16% of all the runners took longer than 8 minutes. And then I just need to find what is the 16% of 200. So 200 times 0.16 gives me
32.
32 runners, not percent, runners. Did you get the same answer using the table? The z-square? We used the empirical rule?
Yeah.
Should we do this problem using the z-score as well? Yeah, let's do that. So this was using the empirical rule. If I didn't know my empirical rule, what would I do? I would find the z-score for these data points. So the z-score would be what? 8 minus 6.5 divided by 1.5. So the z-score is 1. Correct?
Yeah.
Now we are looking for the percent of data above z-score of 1. So the percent of data that is below z-score 1 equals what?
0.8413.
I see. 1. Exactly 1 is 0.84, right?
13.
1. So the percentage of the data below the z-score of 1 is 0.8413. It means that the percentage of data that is above the z-score will be 1 minus 0.8413, which is
1587.
0.1587. See, this is a little bit more precise than empirical rule. Do you see? It's a difference. But if I round this, it will give me also 0.16. If I round to the second decimal point. You see? I could have done it with the empirical rule, but the table gives me more precise answers, right? So the answer would be the same. 200 times 16% equals 32 runners. Do you understand both methods? Yes, ma'am. Good. Are we out of time? Almost. Good job. Mini quiz next time. Please return my, yeah, the laminated. Huh? No backside? Oh, this is bad. Oh, yes. Come on. Come on. Hannah. Hannah not here. Hannah.